So as we have just discussed, BB84 is one specific quantum key distribution protocol. It was, in fact, the first protocol of such a nature to be proposed. I've given a link to the original paper here. It was proposed by two people, Charles Bennett and Gilles Brassard, who were incidentally at IBM. So the details of the protocol have been discussed in brief, and we will be going through the whole process once again. But for today itself, we will only be discussing the protocol without an eavesdropper present. So once we've done that, tomorrow we will be looking at what happens when an eavesdropper comes in, and then there were certain discussions about, yeah, so what happens if Oscar changes basis information, and so those things will be discussed tomorrow. So for today, we will just figure out how to implement a basic simulation of BB84 on a quantum computer. The important point to be noted here, which was also briefly mentioned during the quantum teleportation lecture, is since in both quantum key distribution and quantum teleportation, there is an actual sending of qubits from a sender to a receiver, that is not possible on a quantum computer. On a quantum computer, all the qubits are present in a very specific portion of space, typically called a QPU, or a quantum processing unit. So all the qubits are present on that chip and they do not move from there. Hence, there is no actual sending or receiving of anything. However, we can think of it as sending or receiving, provided we make certain adjustments in our minds. So the basic setup of the whole thing is, as was discussed, that there is a sender called Alice and a receiver called Bob. And they have access to a bidirectional classical channel, which means Alice and Bob can both send classical data to each other in both directions. However, they have access to only a unidirectional quantum channel, which means Alice can send qubits to Bob. However, the other way around is not allowed. So with this basic setup, we want to perform QKD. Now, an important clarification is that quantum key distribution itself is not cryptography. Quantum key distribution is used to generate the keys, which are then used for cryptography. So QKD alone does not give you secure communication. Once you have used QKD to generate a key, then you use some sort of secure cryptographic protocol on top of QKD, which uses the key generated by QKD to encrypt whatever message you're sending. And that is how your communication is secured.
Yeah, Abhishek, if I may interject, just to add to your point. Yeah, so as Abhishek mentioned, yes, the QKD protocol here is a key generation and distribution protocol. The actual encryption is done by what is known as the cipher. And ultimately, the strength of like encryption or security is decided by the strength of the cipher. So here we are discussing the advantages of using the quantum nature of information to implement key distribution protocols. So this is not the entirety of quantum cryptography. Yeah, thank you, Abhishek. Please continue.
Right. So on that note, let's begin. So the idea was that Alice and Bob have decided beforehand that they are going to use two bases. One is the computational or standard basis, and the other is the Hadamard basis. These are also alternatively called the Z and the X bases, respectively. And it was agreed upon that if Alice wants to encode a 0 bit using this protocol, she would choose, depending on her choice of basis, she would encode it using either a 0 or a plus state. So if Alice chose the computational basis, she would encode her 0 bit as a 0 state. However, if she chose the Hadamard basis, she would encode her 0 bit as a plus state. Similarly, for 1, if she chose the computational basis, she would encode her 1 bit as a 1 state. If she chose the Hadamard basis, she would encode her 1 bit as a minus state. Now, note that Alice has two choices here. She has to first randomly choose a state, which will be 0 or 1, and then randomly choose a basis, which will either be computational or Hadamard. For the purposes of uniformity, we have chosen both of these choices in the form of binary strings, so 0 and 1 choices. Now, below is in this code cell, what we have done is there is a random number generator inside of NumPy. We have used a random int function which generates numbers from 0 to n-1, which is why we've supplied it 2. And we're going to generate a string or an array or a list of such numbers of the size of a variable which we're calling numqubits. For simplicity, we're just setting numqubits to be 16. So what this will do is it will generate lists of zeros and ones of size 16. And so we have three different lists which are important here. One is the state that Alice uses. So the one that she wants to encode, this is the 0 or 1 that she wants to encode. This is one set of zeros and ones. Another choice she has to make is the computational or Hadamard basis. This is stored in the variable Alice basis, which is also of the form zeros and ones, and it encodes whether she chooses to encode her state in the computational or the Hadamard basis. And then finally, to end the protocol, we also need to know Bob's measurement basis choices. So that is also implemented in the form of a binary list or a string, where again, 0 and 1 denote the computational and Hadamard bases respectively. Now, so to actually implement this protocol, since there is no sending or receiving of anything, we have to keep the following thing in mind. We will say that the circuit we make, so all the qubits in the beginning are with Alice. So she will encode each qubit depending on her state and basis choices. This is Alice's part of the circuit. Then we can say that she sends her qubits to Bob, at which point we in our head have to believe that Alice no longer has access to the qubits and all the qubits have been sent to Bob. This is just simple as as simple as just thinking that since no operations are that the wire in the quantum circuit corresponds to the qubit going from Alice to Bob, even though there is no actual transfer of qubits in this case. Anyway, so what we need to do is we need to be able to prepare these 4 states, and which we have been discussing since week 1. So it is very easy to make a 1 state. You just have to apply an X gate. If you want to make a plus, you apply a Hadamard gate. If you want to make a minus, you first apply an X and then a Hadamard. And I mean, you don't have to do anything to prepare a 0 state, since all qubits by default start in the 0 state, right? So whenever Alice wants to encode a 1 inner qubit, she applies an X gate as seen here. If she just needs to encode a 0, no action is needed. Then, depending on her choice of basis, if she has chosen the to encode the state in the Hadamard basis, she will apply an H gate. If she has chosen the computational basis, she does not need to do anything. Then we say that she sends her qubits, which will symbolically be represented by the wires in this quantum circuit. And then on Bob's end of the circuit, when we say that Bob has now received the qubits and he will measure it in a randomly chosen basis. So this should be Bob's basis. So this set of numbers will tell us whether Bob has chosen to measure in the computational basis or the Hadamard basis. So depending on what we find in this string, we will want to measure in the Hadamard basis. Now, if you've attempted programming assignment 1, you will see that this was problem 1. The problem 1 was discussing how to measure a state in the Hadamard basis. And we figured out that it was as simple as just simply applying an H gate and then measuring in the standard basis. So that's exactly what we will be doing. If Bob has chosen to measure in the Hadamard basis, we will apply another H gate and then measure the corresponding qubit in the computational basis, or the Z basis as we call it. So for the purposes of this illustration, this is how we'll be going about making the circuit. Now, since there are multiple qubits and we have to perform the same operation on different qubits depending on whether certain things are true or not, we've used loops and if statements. So I'll explain all of these in detail as we go through this, but there is one very important distinction that I want to point out here. You will see that Qiskit textbook also has an illustration on BB84. While their illustration also goes along the same lines, there is a difference between what we are showing here and what Qiskit textbook is showing. For Qiskit textbook, they do not create a multi-qubit circuit, but instead they create many single qubit circuits and then evaluate them one by one. We don't do that here. What we do is we create a multi-qubit circuit and imagine that those qubits are sent sequentially. Since we are not using any 2-qubit operations or 3-qubit operations like C-naughts or Toffoli's anywhere, that distinction is academic. I mean, it does not matter since we are not using any entangling operations, so to speak. All states are factorable, and because they can be factorized, it doesn't matter whether you execute 1 qubit at a time or you do the whole thing in parallel. So in our model of QKD or BB84, we will be having a multi-qubit circuit with the entire bit string that Alice wants to encode and send it to Bob together in a sense. So let's see how we can do that. So I'm going to create a quantum circuit with qubits equal to num qubits, which if you remember earlier, we've set to 16 for now, just so we can see things somewhat. Then what we do is we just follow these 4 steps. So the first thing to note is whether Alice wants to encode a 0 or a 1. That we will find by the corresponding entry in the Alice state variable. So the first thing I have to do is I have to loop through this entire list. So note that all these 3 lists are of the same size. So I can just use a C++ style for loop. This was discussed back in the first lecture during when we discussed Python basics. So this index will loop from 0 to length -1, which is essentially 15. So then I say if the position in Alice, the Alice state list corresponding to index is 1, which means if Alice wants to encode a 1 state, then I will apply a X gate on that qubit, which is step 1 here. If I want to encode a 0, nothing needs to be done. Step 2 is checking which basis she wants to encode in. So if Alice wants to, now this will be found in the Alice basis list, which is also the same size. So we can use the same looping index to go through all of them. So if Alice basis for that particular bit is 1, which means she wants to encode that using the Hadamard basis, then I will need to apply a Hadamard gate on that particular qubit, which is in step 2. So looking at these 3 equations, you can see that this will correctly encode Alice's state in whichever basis she wants to run it in. Okay, and so this is Alice's part of the circuit, which we end with a barrier. Following this, let us now believe that the thing has gone to Bob. So then we need to apply the corresponding basis adjustment for each of the qubits that Bob has received. We do this again with a similar for loop and say if Bob's basis at that position for each qubit that Bob has received, if Bob's basis at that position is 1, which means Bob has chosen to measure in the Hadamard basis, then we apply a Hadamard gate to that circuit at that qubit, which is step 4. So now our protocol is complete. And finally, we just use a measure all to measure, since we are measuring all the qubits. So I will draw this circuit for the basic 16 qubit example. it's somewhat easy to visualize in this case. So if we want to look at this, the first thing we need to look at is Alice's state. So Alice's state has 3 zeros and then a bunch of ones and then a 0, 1, 0, 1, 0, 1, 0, right? So you can see that pattern in the X gates. There are no X gates on the first 3 qubits. Then there are 6 ones and then it's 0, 1, 0, 1, which means it's 0. So yeah, so you can see that there is a Hadamard gate corresponding to every qubit on which Bob wants to measure in the Hadamard basis, and then we measure all of them, right? So as we have done so many times in the lectures previously, we will now run this on a simulator and see what happens. For now, I am going to print everything that was all the results of the experiments. So I'm doing this 10 times. So somebody asked, do I need to repeat this experiment multiple times to know what is happening and what not? To clarify that, I'm going to print this, I'm going to run this 10 times, and every time I'm going to print what outcome I get. So you can see that there are clear differences between all the outcome results that we have got. So at which point we have to realize that we have not yet created the key, because now comes the most important part of the protocol, which is the classical communication. So Alice tells Bob, so one of them will declare on the classical communication channel what basis they chose to measure. And then to get the final key, we only compare bases. We only keep the bits where the bases matched. So to do that, I've put together a little table here showing all the distinct possibilities for what happens for the protocol, right? So if Alice chooses to encode in a 0 state and she chooses to encode it using the computational basis, what the actual state is. If Bob chooses to measure in a particular basis, what Bob's outcome will be, and hence what Bob will call the measurement, his measured bit. Because it is very important to note that if Alice chooses to encode a plus, so she chooses to encode a 0 in the Hadamard basis and Bob measures in the Hadamard basis, then his outcome will be a 0. If Alice sends a minus and Bob chooses to measure in the Hadamard basis, his outcome bit will be 1. It will not be plus or minus, so to speak. And I've also listed the corresponding probability for each and every case. So where their bases will differ, you will see that both the outcomes for Bob are given and their corresponding probabilities. Now, somebody was also saying that we will have very few bits because we are constantly losing bits and measurement and whatnot. So a very simple calculation tells you how many bits you can expect in the key. So what happens is you can say that I will only keep the bits when both of their bases are the same, right? So the probability of them having the same basis means either both have the computational basis or both have the Hadamard basis. And these P's are probabilities. PA is probability for Alice choosing computational, PAH is Alice choosing Hadamard, and so on and so forth. Now, since there are only 2 choices for each person, the probability of choosing either basis is half. So if you do this entire calculation, you will see that the probability through this entire protocol for each bit that their basis match is half, which means on average, half of the total bits will be in the key. And if you look at this table, there is, so there are 4 rows which are relevant here. The first row where both of them choose the computational basis. These 2 rows where both choose the Hadamard and the computational basis, and the final row where both choose the Hadamard. So there are 2 because one of them corresponds to a 0, the other corresponds to a 1. So if you look at the final probabilities for Bob receiving a 0 and Bob receiving a 1, and we consider only these 4 rows because those are the only bits we will consider for the key. So if you look at the distribution of zeros and ones, you will see that it is also equally likely that the key will have zeros as it is likely that the key will have 1, which means on average, half of the bits will be 0 and the other half will be 1. So how do we do this decoding operation? So just for the sake of repetition, I'm going to get the counts by running a new experiment. So, and to show that even if I run this multiple times, I will get the same key, let me keep an empty list of keys. And I'm going to say that, let me call this a temporary key for a temporary key in counts, which means I will be going through this sort of, like these are the results for each time I run this, if I run this 10 times. So I'll be going through one of these every time. So each time temp key will be equal to one of these rows. So for temp key, let me begin with an empty string, which is the key. Then I will go through every qubit one by one and compare the two lists, Alice basis and Bob basis, at that position. So if for the ith qubit Alice sent, Alice and Bob chose the same basis, I will add that particular bit to the key. And then I will append this key string to my empty list of keys. So once I do this, I should get 10 keys or so. So we will have a look at that. I should get 10 keys because I should get a key for every time. So once I've run that, I will come to why this has happened in a bit, but yeah. Once I've done that, for every key in key, let me print all keys. Okay, so you see that all of them are the same, even though all of these were different, because these were just the measurement outcomes from Bob. Once they have declared their bases and actually created the key, you can see that irrespective of how many times I run this protocol, I will always get the same key. Keeping in mind that when I say I'm running this again, I am encoding the same state using the same bases, and like the basis choices for Alice and Bob do not change because I have declared them at the beginning. If I change their basis choice, their keys will change. But the quantum randomness, so to speak, does not affect the key itself, because when their bases are the same, it is guaranteed that they will measure the same state. So there is no issue of randomness in that case. And when their bases don't match, there is no correlation that I can say about what state I have sent and what state I have received, because in either case, the probability will be half. So by keeping only the that my key is reproducible, irrespective of how many times I run the thing on a quantum machine. Now, I said that the key length should be half, but here I'm getting a key length which is 1/4. So what's going on? And again, not half zeros and ones. Again, note that I say on average, and this is a very important part of the whole thing. So if I, now for the sake of theatricality, let's say, if I say I have 2000 qubits, which I want to send. Now, clearly there is no quantum computer on Earth right now that we know of that has 2000 qubits. There is an annealer by D-Wave, but that's a different piece of hardware, as was clarified during this week's seminar. But suppose I'm trying to generate a key out of 2000 qubits. So again, I can't print 1000 bits, but you have to take my word that I will be using this. So I'm not going to draw it because it will take an inordinate amount of time and there'll be nothing coherent from that. But I'm going to make the circuit for it. And then I'm going to run this sort of, run the circuit and then get the keys out of it. So now what you see is that the length of the key is 1008, which is roughly half of 2000. And there are also 530 and 470 zeros and ones respectively, which is again close to half. So this is what I mean by on average. So the larger number of, this is just statistics at this point. This has nothing to do with the fact that we're using quantum distributions or anything. This is just statistics. So the more bits you have, the closer to the average distribution you will get. So this fact of the key being roughly half the number of bits is true. And also the key being made of roughly equal numbers of zeros and ones is also true. And this is very important for cryptographic reasons, because if there were either greater number of zeros or ones, that would mean I could just randomly guess a larger part of the key just by using an all zeros or an all ones key. Again, I mean, not practical significance, but there is a theoretical relevance to this matter. So with that discussion, we can see that why this BB84 protocol was hailed to be such a great thing, because it provides us a way of generating secure keys between two parties. Now, as Professor Gangopadhyay pointed out, the QKD protocol itself is not enough. There have to be other, so a whole cryptographic solution is more than simply a set of protocols. There has to be authentication and several other steps before any of this goes on. Now, so far we've discussed the case when there is no adversary or there is no Oscar, so to speak. When Oscar comes in, there are several other problems, but an advantage of this BB84 protocol is that it gives us a way to check if any tampering has been performed. So we will consider one specific case of such a tampering or such an attack tomorrow. And with that, I'm going to conclude today's session. This notebook has been put up on GitHub. Please go through it and try to generate your own keys and see what you get. Just for the sake of comicality, let's try to print all the keys. So now these are 1008 character long strings, but you can see that they're the same, which just adds to the point that I was making earlier. But anyway, yeah. So with that, I'm going to end today's session, and now we can take questions.